What's up, everybody? It's Miss Wesley, and welcome to day one of probability. We finally made it. As you can see, I'm in the video now because I started using a new program to record these. So I hope this goes well, and I ask for your forgiveness in advance just in case I run into any technical difficulties. I'm going to try to make this as easy to follow as possible. So you'll notice we're in a new packet, and you might want to just get your own copy to follow along with as we go through the video, and I'll kind of help you fill the notes in. And it starts with counting principles and permutations. So I wonder what comes to mind when you see counting principles and permutations. Today's going to be fun because we get to look at some real life scenarios where some math is going to come into play for permutations of things. I would suggest you read the warm up and pause the video and make your own guesses as to what you think the answer might be before you turn it back on and then kind of compare it with what I do with you. But I would do that now. And now let's go through it. So it says that it's lunchtime and we get to head to Shake Shack. And I was looking at the Shake Shack menu. There are 4 different choices of burger. So a Shack burger is the one that I get. Smoke Shack, I forget what the difference is. I know Shroom Burger is meatless, or you can get a chicken one. For your fries, there's regular cheese fries and bacon cheese fries. And then for dessert, there's shakes, floats, cones, and I must have not seen this on the menu, a concrete. I looked up what it was. Frozen custard with blended mix-in sounds delicious. I feel like I'm gonna have to get there ASAP. But it says, in how many different ways could you select one of each of those things? So a burger, fries, and dessert. So if my order is gonna be what? A Shack burger, regular fries, and a shake, I guess, a chocolate shake. That's one different, one arrangement of those 3 items. But you could probably go through a lot more, right? You can get a Smoke Shack with the shake and the regular fries, or you can get another burger with the shake and the regular fries. So we want to find a good, convenient way to do this so that it won't take too long to figure out. And I kind of like a blanks method for this. You might want to just draw 3 blanks. One for the choices you have for burgers. We have 4 choices for burgers. One for the choices that we have for fries. So what do we have? 3 choices for fries. And then one for the choices we have for desserts. There's 4 different types of dessert choices. I'm wondering if you can guess what we're going to do to these 3 numbers to get the possibilities. And I'm hoping you're going to guess, and this is called the fundamental counting principle, that we are going to multiply those 3 things together. If you can choose a burger in 4 ways, fries in 3 ways, and a dessert also in 4 ways, you can multiply the 3 together, right? We'll multiply the 3, we'll get 48 total ways that you can order those 3 things at Shake Shack. And I could have you write out all the total possibilities, but that would take a long time. Let's summarize this. We're trying to find convenient ways to do this. It says fundamental counting principle. It must be important because it's a fundamental principle of something. Whenever something gets that name fundamental, I take special notice to it. It says for a sequence of 2 events in which the first can occur in m ways and the second can occur in n ways, the events together can occur kind of like we just did it in m times n ways, in the product of m and n ways. So there's a little bit easier of a tree diagram here that didn't take too long to write. Let's say you just have a scenario where you have 3 pairs of pants to choose from in the morning and 2 different shirts. How many possibilities is that? Here are the 6 possibilities. Pants 1 can go with either shirt. The second pair of pants can go with either shirt, and the third pair of pants can go with either shirt. And if I count those up, 1, 2, 3, 4, 5, 6, it confirms that I could have just done 3 times 2, right? 3 times 2 equals 6 possible outfits. I want you to keep that in mind because the rest of the worksheet is going to have us come up with a bunch of different number of ways that certain things could happen. Okay, let's see. A home alarm system consists of 4 digits, 0 through 9, that can be repeated and must be entered in the correct order. That's important too. Today we're talking about orders and ways to arrange things as well. And we're going to get some vocab that goes along with that. I still continue to like this blanks method. Can you draw a blank for each digit? 1, 2, 3, 4 blanks. And in the blanks, we're going to fill them in with the number of possibilities that we have for the digit for each of those blanks. Well, if it's 0 through 9, that's how many digits, right? 0 counts as 1, and then the numbers 1 through 9. That's 10 possibilities for the first digit of the code, 0 through 9. It says that the digits can be repeated. So let's say I pick a 3 for my first digit. I still have all 10 choices for that next digit. So 10 choices for the second digit, 10 for the third, and still the same 10 for the 4th digit. Believe it or not, with just a little 4-digit PIN number, there's 10 to the 4th amount of ways you can construct that, a 1 with 4 zeros. So 10,000 different ways you can make one of those codes. What do you guys think about my handwriting? Not so good, huh? How many okay, so some more stuff about codes. 2 says, how many 4-digit codes are possible if no numbers can be repeated? I want to do this with blanks again. Well, what's the difference here? You still have 10 choices for the first digit, but once I've picked, let's say, a 3, 3 is off the table. I can no longer use it. No repeats. So we're going to say 10, then I only have 9 choices, right? Does this look good? 8 choices, you've taken one away, 7 choices, and I'm just going to multiply that. So I'll go 10 times 9 times 8 times 7 to get 5,040 ways. Okay. So that is drastically reduced if you can't repeat. How many 4-digit codes are possible if no numbers can be repeated and there's an extra stipulation? The first digit has to be even. We'll use your blanks. Make the first digit an even number. We've got to count up the number of even digits there are, and then we'll see what else we have left. Even numbers, 0 through 9. So I know 2, 4, 6, and 8 are even. That's 4 of them. Is 0 even? Yes, 0 is an even number. It's neither odd, it's neither positive nor negative, I should have said, but it is even. So there are actually 5 even possibilities. 0, 2, 4, 6, and 8. Let's say we picked 2 as the first number, and 2 is off the table. Think of how many choices you have left for the next digit. It can be any of the other digits. It just can't be a 2 because of no repeats. So we have 8 choices left. And actually, I should have said we have 9 choices left. Let's see if I can practice with the delete key. Should have said 9, right? Because there's 10 total digits and we took 1 off the table. So let's go with 9 there, then 8 once you've used the next one, then 7 once you've used the next one. Go ahead, type that in. 5 times 9 times 8 times 7. You only have 2,520 ways you can do that. All right, are we having fun yet? Let's look at 4. A 10-digit pin, this is going to be a lot to write out, consists of each of the numbers 0 through 9 with no number being repeated. How many of these pins exist? Well, 10 blanks are going to have a lot of writing. 10 times 9 times 8, I'm already getting tired, times 7 times 6 times 5, this is too much, times 4, 3, 2, times 1. That's going to take a long time to type into the calculator, and it sure took a long time to write. So I was wondering if you knew of any shorthand for this, writing down the product of the consecutive digits from 10 all the way down to 1. And that here comes factorial notation. If you see, I'm going to rewrite this. I'm going to actually get rid of that question mark. Maybe I'm not. I'll just cross that question mark out, and I'll write it as 10 with an exclamation point. This is not me shouting 10. It's me using 10 factorial. And the way we can define that is that n factorial, let's see, we'll put it in red here, n factorial is going to equal n times 1 less than n, right? After 10 we went to 9, so n minus 1 times the next one, n minus 2, and so on and so forth. I'll put an ellipsis here, a dot, 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 until you get down to maybe like a 3 and a 2 and a 1. As soon as you hit 1, you wouldn't go to 0, right? Wouldn't make sense to put a 0 there and the whole thing would get wiped out. But all the consecutive digits multiplied, or the consecutive integers multiplied, from the highest number down to 1. There is a little catch here, 0 factorial. So you know how, what do we say in exponent rules? Anything to the 0 power equals 1. And there's a reason for that. That's because if you want to raise a fraction to a 0 power, then you don't have an undefined denominator. But I wonder what they would make 0 factorial. It feels like that should just be the number 0. Unfortunately, because of what this says here, they actually define 0 factorial to be the number 1. And that's a definition just to memorize. Why is it 1? Well, it says under here, a collection of n different items can be arranged in n factorial different ways. So case in point, 10 digits can be arranged in 10 factorial different ways. Well, how many ways could you arrange 0 items? Like, how many ways could I take no items and arrange them? Not in 0 ways, in 1 way. There's 1 way to do that, and you just don't arrange any of the items. So they call 0 factorial 1, and we'll keep that in mind. If it comes up later to help us, we'll come back to this. 10 factorial, we'll get it into the calculator. I'll tell you what it is for now, but we'll talk about other ways that we can get to this a little bit quicker. 10 factorial is huge. It's actually 3628800. So it's in the millions, 3,628,800 ways you can make a 10-digit PIN number. Maybe all of our PIN numbers should be 10 digits so that nobody can hack into our stuff, right? But that's a lot to type in. Now, let's just have some fun practicing with factorials. What do you know? What could we do without a calculator? I bet we could try all these three. And there's a slight change. I think I need to make a number 7, but let's look at 5. 5 says 5 factorial. Well, I could expand it out. It's 5 times 4 times 3, 2, all the way down to 1, even though you don't really need that 1 at the end. So 5 times 4 is 20, times a 6, right? 120 should be 5 factorial, not too hard to get in your head. This one, 6 factorial over 4 factorial. I'm claiming that we could do this pretty easily if we expand it out. Can you write this as 6 times 5 and then go all the way down? Times 4, 3, 2, 1. And on the bottom, don't you get some of those same numbers so that stuff should cancel? I have the 4 factorial part of it, so I have the 4, 3, 2, 1. And that's kind of cool. That's going to make this easier to simplify because the entire 4, 3, 2, 1 part is the same on top and bottom with 1s left over in their spots. So 6 times 5 is all that's left over, and you get a 30 for number 6 without too much work. Okay, number 7. In your packet, number 7 should look a little different. I wanted this one to be 17 factorial over, if you don't have this change, make it now, over go 14 factorial, and then times 3 factorial. Sorry, that thing is bouncing. Okay, I think I made it go away. So this is very sloppy, but make it 17 factorial over 14 factorial times 3 factorial because I want to try something. So up top, I'm not going to write out the whole thing, 17 down to 1. I'm going to make it 17 times 16 times 15. And then can you just put after that a 14 factorial? Because I'm just anticipating the rest of that canceling with the 14 factorial that's on the bottom. So part of 17 factorial is 14 factorial. On the bottom, now that I changed it, you have 14 factorial times 3 factorial. Well, the 14 factorials completely cancel. And 3 factorial, I know, is the number 6. It's a 3 times a 2 times a 1. So what I could do here is, let me rewrite this one more time. So 17, 16, and 15, I think we had, right? And then on the bottom, 3, 2, 1, I'll just write that as a 3 times a 2. And if you don't want to reach to a calculator, I don't think you have to. Reach to see what things cancel. So 3 goes into 15, we could say. 3 goes into 15, 5 times, so 1 and a 5. And 2 goes into 16, 8 times. So if you can do 17 times 40, right, it's a little bit simpler than typing that whole thing. And 17 times 40, I'll let you know, is going to be 680. And that one gets simplified. Okay. Moving on to the next page. Now we actually get to see what that word in the heading meant, permutation. It says an arrangement of items in a particular, can you fill in the blank, order. Order is a big deal with permutations. Order really, really matters because you're talking about arrangements of things. What things are we talking about? Number 8 says, in how many ways can you arrange 8 shirts on hangers in a closet? So I've got my shirts in the closet. I could maybe just write one blank for each hanger or each shirt. So I could do 8 times 7 times 6 times 4, 3, 5, 4, 3, 2, 1. So 8, 7, 6, 5, 4, 3, 2, 1. That's the way we would have done it on the front of the worksheet, and that's the counting principles way to do it. But now we've got a shorthand. That's the same thing as just saying 8 factorial. And there must be a shortcut for this in the calculator. So I wanted to show you that before we go. You're going to go in your calculator. I'm going to pull this up and see if you can see it on this calculator simulator. You're going to hit the 8 first. So type in 8 on your calculator, then hit the math key. And then what do you think it's going to be? We've used a lot of stuff in the math menu. Can you go over to probability? P-R-O-B is going to be the probability menu. I'll just scroll over to the right. And then there it is. Pay attention because we're going to use a couple different things in this list, but let's use number 4. And this should be 8 factorial. And we can write it as 40,320. 40,320. So it's math, probability, and then the factorial key. And how many ways can you arrange all the letters of the English alphabet? Use your calculator for this. There's 26 letters. So do 26 factorial, which is huge. And we'll come back to that in a second. Okay, till next time.